Hello and welcome to this tutorial on T3D 1.11.5. Today's goal is to recreate the scene that we see in this video here, which is basically composed of a point cloud, a dynamic point cloud that is driving a fluid simulation. And we render the fluid simulation using the volume T3D, and we compose it also with with instanced boxes on the point cloud. Before we get into that, I just want to give you a quick overview of what's new in T3D 1.11.5. So let's have a look at this. The first change is the Geo to T3D, which is basically the successor to the SOP to T3D that we had before. So let me quickly install T3D here. I don't have it installed yet, so I'm just dragging and dropping T3D into the file, into the TouchDesigner network, and you see that it's available here now. And there is a new Geo to T3D, which is replacing the SOP2 T3D and is more generalized, as in it has two inputs here. It has a SOP input and it has a POP input, but you can also still just define a geometry here, geometry comp. And it does exactly the same thing as the SOP2 T3D did. So it takes in any meshed geometry. In this case, it's a little simulation that I prepared in POPs, or not a simulation, a little animation here. And it converts this into a 3D texture. So it renders that into a 3D texture. More specifically, we need to define the bounds in space. So let me display the bounds. The bounds are here now visualized with this yellow box. And if I were to change the upper bounds, for example, or you would see that. So the box represents the bounds I've defined here in space, and that region will be rendered to the 3D texture. So if my animation would live somewhere else, so outside of these bounds, we will not see anything. We won't see anything in this 3D texture, but only if we really have the bounds aligned with the geometry that we want to render into the 3D texture only then do we get a result in here. So that's basically the main purpose of the Geo to T3D. It allows us to convert geometry in real time to a 3D texture. One thing that I want to mention about this, which is new, so I'm doing some blurring and compositing. You can have a look at this if you get the file via my Patreon. But I'm just using this T3D to render it as a volume. And I wanted to show you that you might want to kind of render both the T3D volume as well as the original geometry. So if I were to also render this, you would see that the geometry is, it's between -1 and 1. So it has a size of 2 in X and Z. And that's also the bounds I defined in the Geo to T3D. But the volume will by default always be scaled such that the volume T3D will be scaled such that it has side length of 1. But if we want to align these two, we kind of need to take care of, we need to tell the volume about the transformation that comes from the bounds we defined here. And I've built a method now that automatically allows us to do this. So we can turn on the pre-X form and then tell our volume that it's supposed to look at Geo2 1 and get the T3D transform format. And that will make it such that I should maybe also then make the light further away. Put the light further away. That these two are now scaled. So if I were to change my bounds in any, I don't know, maybe I scale the margins such that I cover a bigger space, a bigger part of space, it will always move or scale and transform the volume in general to be aligned with the geometry that came in here. Okay, I think that's about it, about what I want to say about the Geo2 T3D. And we can move on and have a look at the new Metaball T3D component. And the Metaball T3D is basically, I think there is also a Metaball SOP that exists. I've never really used it, to be honest, but it allows you to define multiple spheres with positions and radii, and then smoothly blend between these spheres. And in this particular case here, right now, I have a point cloud right here that is defined in pops. Each of these points, they have some attributes, but they do have a position, of course, and they also have a point scale attribute. And position and point scale will be used by the Metaball T3D to define those spheres. And then we can use the group strength to define how strongly they should be merged together. I'm doing some other effects here. Let's look at only the 3D texture. So yeah, we can smoothly blend these spheres together. So like if I reduce the group strengths by a lot, we would only get those spheres. Here you go. And then if I introduce some goop, let's go ahead, they will be blended together. So yeah, this is the new Metaball T3D. That is what it is good for. And you can define these spheres either by pops, if you have a version of TouchDesigner running that supports pops. And otherwise, you can also do it using tops. If you use tops, it will use the red, green, and blue channel for the XYZ position and the alpha channel for scale. And if you use a chop, it will use the first 3 channels for the positions and the last channel or the 4th channel for the radii. Okay, and yeah, then you can do anything else here. You might rotate it, scale it up and down. But yeah, this just returns then a 3D texture representing these metaballs. And we can, in this case, I'm just directly rendering this using a surface. And another really exciting thing that exists as a bridge between 3D textures and pops is the polygonize pop, which, for a more simple example, allows you to take a 2D image, for example, of this banana, and convert it into a mesh. Let's give it some, yeah, here we go. So now I need to define a proper threshold, and then it will draw the outlines of whatever this image is. So let's take a different image, for example, that one. Depending on our threshold, it will draw that image as a mesh. And we can, I don't know, we can also fill that 2D surface and maybe invert it if we feel like it. But if we zoom in, it really creates triangles of that, like creates a mesh for this image. But the amazing thing is that this works out of the box also with 3D textures and converts a 3D texture into a 3D mesh that you see right here. It doesn't have normals, so we need to use a normal top afterwards. Yeah, and we can just out of the box get a 3D mesh from the 3D texture, which is amazing. I did downscale my 3D texture a bit on purpose to get this like coarse wireframe around my 3D texture here. But if we don't do this, we can also get a really like high quality mesh with only 2 milliseconds. I think that's fairly quick. Yeah, so I think this altogether is quite a strong like bridge between T3D and pops, because you can convert pops into T3Ds with the Geo to T3D, and you can also convert T3Ds to pops using the polygonized pop. And from there, you can do all kinds of things. Of course, the point cloud T3D will now also support pops as an input point cloud. And the advect T3D will also support a pop point cloud for advection. And the sprinkle T3D can also sprinkle into a pop point cloud if you feel like it. So yeah, I really did my best to connect the two operator families, and I hope you have fun with it. Maybe just start by exploring these small patches that I've created here. You can get the project file on my Patreon. But now I want to move on and recreate this scene here. So first thing we need to do is to define some dynamic point cloud. I will delete that video and start from scratch right here. We will do this now in Pops. You could do the same thing in Tops, but I think it's time for all of us to learn Pops, and yeah, hence I'm using Pops right here. For those of you who have never heard of Pops, Pops are basically a very similar thing to SOPs, so they are for geometry processing, but everything is processed on the GPU, which comes with insane power, so it can all be executed in parallel and highly optimized, but it also needs a specific way of thinking, and maybe the operators might be confusing in some cases. For example, the math combine might seem a little convoluted, but they are really powerful, and I can only motivate you to take your time and look into all of this. And I personally hope that I can, in another video, maybe convince some of you to give GLSL another chance in Pops if you are not convinced of GLSL in Tops yet, because GLSL in Pops is maybe even easier than in Tops, I would argue, and it's really powerful. But we won't use any GLSL today. We will start with a point generator pop. So this allows us to choose a shape out of this drop-down menu. I will use a sphere, and we can define a number of points that we want to be in this sphere. Let's go with 100,000 points maybe for now. And we just generated 100,000 points. You can middle mouse click on this and get get all the information that you can gather here. And you can also convert this always to a DAT and have a look at what exactly we are looking at. And you will see that currently each point has a position attribute as well as a normal attribute. And I can tell you that we don't need a normal attribute for this patch, so I can actually go ahead and turn that off just for optimization purposes. Okay, I will get rid of this, and I want to move those points around. We could build some more interesting particle simulation potentially, but I want to focus rather on the bridge to T3D, so I will just use a simple noise pop to move my particles around. So the noise pop takes in a lookup attribute, or like it takes in a pop, and then you can define a lookup attribute. And currently based on the position of each incoming point, it will calculate a noise field. And then we can define what we want to do with that noise. Currently, it creates a new attribute called noise, which you can also see down here. It has changed position and noise. And if I middle mouse click on this, you will see that we have 2 point attributes, the P for position and noise. I actually don't need the noise attribute itself, so I can turn that off. But I do want to add noise to P, so maybe let's animate that noise by writing me.time.seconds times, I don't know, 0.2. And then these points will be displaced by the noise, and we now see the movement that comes from it. I will reduce the harmonics a bit, maybe turn it to 1, set it to 1, but increase the amplitude quite a lot, and maybe the period. I will play with this later, but we do now have a point cloud that moves through space. And we will use this point cloud and insert the position of those points into our fluid T3D as substance, but we also want to get the velocity of these points at each time to use the velocity of a point as a false input to the fluid simulation. Long story short, we need the velocity of these points. So how do we get this? The idea is that we remember the last position of the points using a cache pop, where we need only a cache size of 1. I only need to remember 1 frame of this pop, and I'm outputting the last frame as well, so that 1 frame that we stored. So I'm outputting index -1. So this pop is now just always 1 frame behind its input. So we have the last position and we have the current position, and we can calculate the velocity based on this by subtracting the current position from the last position. If you're somewhat familiar with linear algebra or vector calculus, that might be intuitive to you. If not, I would just recommend you to search for a good YouTube video on this. But that gives us the velocity up to a scalar factor that we can accomplish for as well. So what we want to do is we are going to use a math combine because we want to subtract 1 position from the other one. Subtraction is a math operation. And if you look into POPs, you will see that there are actually 3 different math operators. The first one will allow you to the first one's really simple, maybe to the math top, I would say. So it allows you to just scale the values and add constant values to a specific attribute, while the math combine and math mix POPs allow you to take different attributes together and perform complex math operations on them. And in this case, we want to take 2 attributes and subtract them from another. The way this math combine works is that you first abstractly define this operation you want to do with these placeholder variables a and b, and then you tell the math pop what a and b is supposed to be. So a is going to be my input position, and b should be the second input's position. But I don't have this accessible here yet, so I will go into inputs and say that I want to, so it's currently getting all the attributes from the first input, but from the second input, I also want to get, well, I don't need all the attributes, but I do need the position. And then I can go back to the combine and now choose P1, and that is going to be the P from the second input. Or we could also maybe rename it here for clarity to last P for last position. And then I can choose last P. And the result is currently written to P, which doesn't really make sense. This is supposed to be our velocity, so I will call it V. And now our pop has a new attribute called V, and we can kind of visualize how that attribute looks like by turning the viewer active on that pop, right-clicking on the background, and going to display attribute. And then we have a couple of options. And because this is a velocity is a vector, it makes sense to look at the vector as at the attribute as a vector. So I will turn on V for the velocity. And now you see that I have all those little arrows here. I will actually reduce the number of points to make this more obvious. So at each point, I now have a vector visualized that shows me the velocity, hence the direction that particle is moving in. So this seems to be all correct. We do get the velocity. To be precise, the velocity is not scaled correctly. And let's fix this maybe by multiplying. We want to multiply the velocity by our frame rate to get the correct velocity. So I will do a times b, where A is my velocity and B is going to be my frame rate, which I don't have accessible here at the moment. And I can declare that as a uniform. All this might be new to you, but I will call this U rate for uniform rate. It's going to be a float and it will be me.time.rate. This is called a uniform because what we are doing here is basically writing GLSL, but we don't rewrite the code. We just tell the operator what kind of code to write, and this makes it easy for us. But once we have declared the uniform here, we can use that value as a scope here and say that we want to multiply V by U rate. And now V has the correct scaling. Okay, so this is good for now. Maybe before we move on to converting this into 3D texture, we should first set up our rendering and render this as a point cloud. So we will need a geometry and I want to render this as boxes. So I will go into the geometry, delete the torus and drop down a box and turn on the rendering and the display. So we do have one box and then we can instance that box based on a pop. I will create a null here and call it instance data. And then we will instance that box based on that instanced data using the position as the translate. So we see a bunch of instances of this box. Obviously, the box is too big. We could go ahead and scale the box down right here, but instead I would like to use the scale instance attribute here basically. But we only have the position and the velocity and none of both are reasonable attributes for scale. So let's create a new one here by using the attribute pop and creating a new attribute using not a custom one, but the predefined point scale attribute is fine for us. And here I can just set a small value of maybe 0.02 going to my geo and using that point scale attribute as the scale in all 3 dimensions. Now I do get small boxes here. Okay. Maybe I want to make them a little bit bigger. That seems more reasonable. Okay, next thing might be a camera from which perspective we want to render this and a render top to actually convert that into an image. And I will connect an out here, turning the viewer active on that out to see in the background what we're doing here. And just to set up a more interesting rendering, I will drop down a light. I will move this to a position of my choice, 5:1. I will set that light to be a cone light, and I will use a null comp, drop it onto the light and set it as the look at, such that the light now looks at wherever that null is. So I can move it. I will just leave it at 0, but I want the cone light to look here. I will increase the cone light's viewing angle such that it covers the whole point cloud. And then I will go to the shadows tab and turn on soft shadows with a decent shadow map resolution. So we're getting some more interesting renderings in a second. I will go to the camera, go to its settings and set the background color to have alpha. And yeah, this looks better, but not perfect. I think the fact that the boxes are all aligned towards the camera is a little bit boring. So I could, for instance, go to the instancing tab 2 of my geometry and use the velocity as the rotate 2 vector. And now those boxes will always follow their current direction, like the direction they are moving in is also going to be their orientation. Maybe that's already a little bit more interesting. We should also declare a proper material. Let's use a PBR on those boxes where we might want to reduce the metallicness, and maybe the roughness to our liking, such that we get some sparkling, and I will increase the base color such that we can see more of them. And I also don't like the fact that they all have the same size. So let's use a random pop, which allows us to randomize the values of a specific attribute. By default, this will add the random values to the position attribute, which I don't want to do. I want to multiply the random value with point scale. So whatever the incoming point scale is, I'm going to multiply it with a random value generated right here. I want the random value to be something between 0.1 and 1. And I might want to use a different seed here, such that the random number generator is not the same as the one that we use back here. Okay. Yeah, maybe a little bit dark. We might want to set some emit color on those boxes as well. Yeah. Actually, those boxes are not the focus of this video, so let's move along and convert these boxes, this point cloud, into a T3D. Before we do that, I will go back to using 10,000 points, so we do see a little bit more happening right here. Okay, so we do have some boxes flying through space. We have this point cloud. And now I will use the point cloud T3D, the updated point cloud T3D, which has a pop input. So we can just go ahead and plug that into the T3D. And we do see something happening in that T3D. Definitely some points visible here. And to move on from here, let's actually use a volume T3D so that we can see what is happening, what this point cloud, what this T3D currently looks like. I will turn off, whoops, I will turn off the geometry, the rendering of the instanced boxes for a second and look at the point cloud, only the point cloud, and get the correct bounds. Again, let's display the bounds of this T3D, and we see that the point cloud, I don't know if you can see it in the video, is bigger than the box we are currently working with. So let's increase the upper bounds and lower bounds to be between -1 and 1. And that should get most of the point cloud into the 3D texture. And now we can also see that in the rendering that we're getting, that we get most of this. Maybe we actually want to go from -1.5 to 1.5. Oops. Here we go. And we can also increase the max axis resolution to be 128. So we get a more refined point cloud. Yeah, okay. So we do now have that point cloud as a volumetric rendering that I really like. And yeah, we could maybe already go ahead and try to composite both the rendering of the boxes as well as the volumetric rendering in one rendering. Currently, we see that there's a scaling issue where the volume is too small and the depth is not correctly composited. Let's work on the depth compositing first. We can, there's a simple solution to this because the volume T3D has a depth compositing parameter. And if we turn on that toggle, it will take care of the depth compositing for us. But we need to make sure that we then kind of forget about the output from the render top that we are using and use the output from the volume T3D. And now the volume is being rendered in there. It's just too small. Like if I would scale the volume up correctly, so then you would see it. It now aligns with those boxes, and it is also, the depth is correctly composited. So I now also fixed the scaling already by setting this uniform scale value to 3. But this is not the recommended way to do the scaling, I would say, or more generally the transformation. Instead, I would recommend to you to go to the XForm, pre-XForm tab, turn on the apply pre-X transform, and tell this volume geometry to get the point cloud 1 and its T3D transform, which is a method that I created in the last version. Transform, whoops, typo. And that will automatically calculate the correct transform to scale the volume and move the volume such that it is aligned with the bounds that I've defined here. Cool. So now this is correctly aligned and depth composited. I think this could already be quite an interesting effect. We could maybe use a constant T3D here, and what color? Well, maybe we should set the pixel format to 16-bit, and we could make this non-grayscale the value. I don't know. Let's play around with it. Something like that. And then we already get a more interesting like color gradient based off the light that falls through the volume. As you can see here. But we also see that the volume looks a little bit pixelated. That is because the point cloud really turns on and off individual pixels here, as you can see. And it's not really a smooth object. So let's, I will turn the pixel format to 32-bit mono on the point cloud and then use a blur T3D, which with maybe 2 passes, and then go on with the rest. So now this is a smooth, like, yeah, a smooth density field around those boxes. I think that looks more interesting. And maybe I will scale that I could scale the alpha up a bit, and yeah, we get more density. So this already looks quite interesting, but I don't want to, I wanted to go a step further and kind of have this density field transported with the velocity of that point cloud. So let's use a fluid simulation for that. I will drop down the fluid T3D. It has 3 inputs, 1 for forces, 1 for obstacles, and 1 for substances. And we are going to plug in the currently created T3D as a substance here, and then use not the velocity, but the substance output of the T3D and connect that to our volume. This first of all looks broken. I should reset the simulation once. And now we see that it just accumulates more and more substance, because in each frame it gets the current T3D that we plug in as a substance and adds it to the current substance. But we can go to the substance tab of the fluid simulation and increase the dissipation, which will over time like reduce that value again, the density again of that substance. And then, yeah, it doesn't just get more and more, which is reasonable. And now I also want to get the velocity of that point cloud as a force input to my T3D. And here it gets a little bit tricky. I will render that point cloud again to T3D, but this time I'm not going to render it in grayscale as we did right here, but I will render it in color, where the color is going to be the velocity of my point cloud. In order to do so, I should actually use an attribute here. Yeah. Well, I think it will be easier to use a math combine. Well, I'm sure there are several ways. I will use a math combine and just say operation is going to be A. My scope is going to be V, and I'm basically just renaming this to be the color. It should be color.rgb because I only get 3 values from velocity x, y, z, and then I can only write to 3 values. And now this point cloud has a new attribute called color, and the red, green, blue values of that color will be identical to the velocity. The operation operation just A does nothing but copying this value to a new value, a new named attribute. And if I connect this to that point cloud, T3D, it will use this as the color of my pixels here. Although I need to make sure that the pixel format is non-monochrome, but should be maybe 16-bit float RGBA. And then you see, yeah, the color is actually brought over. And then we maybe should also blur this velocity field that we basically generated by a bit. And then we can use this as a force input into the fluid simulation. Wow, okay, so this definitely moves the fluid around, the substance around. Maybe it's a little bit too fast. That is because we kept the alpha scaling in the point cloud here. So maybe let's reduce this to something like 5 or maybe even just 2. Yeah, this is, yeah, depending on the vibe you're going for, this seems more appropriate for me. Cool. And yeah, at this point, we are basically done with the tutorial. With what I wanted to achieve with this tutorial. We can maybe play around and create a more interesting point cloud. But I really just kind of want to leave this up to you. Maybe just to show you that if I were to use a transform and move the point cloud left and right, it will really also move the fluid left and right, as you can see here. Same with up and down. So the particle's velocity drives the fluid simulation, right? So this is what I wanted to achieve here. And in the fluid T3D, we can maybe increase the pressure projection iterations a little bit just to increase the quality of the fluid simulation, but make sure that you kind of get the right value here, because if you increase this by too much, you will drop frames eventually. This is, yeah, more expensive the more iterations you do. And we could also turn on the vorticity confinement, which is kind of a math trick to illustrate more refined velocity, more refined fluid simulations with more vorticity in it. Yeah, and then using the dissipation, I set this to some magic numbers. I don't know if you have all these 3 numbers at the same value, and maybe let's also set the initial color of the substance to be white, then this will just be a grayscale fluid. And then this dissipation values controls the red, green, and blue channels of the substance, how quickly this dissipates. And if, for instance, I reduce the red value here, that makes sure that the red stays longer in the fluid. And because of that, you will see you will see a certain gradient that comes from the red staying for a longer time in the fluid. And you can play around with this to find colors that are interesting to you. Okay, I think this is about it. I hope you found it interesting, and I'm looking forward to seeing what you make with this tutorial. Please tag me on your publications so I can find your creations. And you can also just download this project file on my Patreon. And maybe you're also interested in the small snippets I showed you in the very beginning. Thanks a lot for sticking around, and looking forward to seeing your creations. Thank you. Bye.